Yes, I'm the guy. For salts and esters, we have these diagrams here. This is the glucoheptonic acid. This is lactobionic acid. We have lauryl sulfate. And stearic acid. We also have this the propionyl group. We said that erythromycin is insoluble in water because of this part, the amino group. And we say that this R group can be modified and we put an alkyl group to make esters. For example, we can put a propionyl group here to make an ester. And this ester increases the lipophilicity. So the ester of the propionyl erythromycin will be more lipophilic than the erythromycin itself, or will be more water insoluble than erythromycin. Also, we can make salts. From this, we can make salts. For example, we can have the glucoheptonic salt. Now, this one will be this H. So this one will be minus. And this one will have the H. So we shall have this with H. This one will be plus. This is the glucoheptonic ester. Glucoheptonic salt of the erythromycin. As you can see, this ring is lipophilic, or it is less water soluble, as you can see. Now, addition of this group, we are seeing the hydroxyl groups, many of them, meaning that this salt increases the water solubility. If we increase the water solubility, meaning that this one is not suitable for oral administration, meaning that this one will be for parenteral use or IV administration. So it is for IV administration. Because it is highly water soluble, reduces the bioavailability if it's taken orally. Same for lactobionic acid. Lactobionic acid also it will be minus. This one will be plus, the H is taken. So these salts, it's the same, it also increases the water solubility. And it's given also IV. We are going to see why, because erythromycin is destructed by acid, as we are going to see. These ones bypass the acid. You can have the erythromycin stearate, which is a sort of the erythromycin. This one will be minus now. But as you can see, we have the polar group here, but this chain is too long for it to be water soluble. It is lipid soluble. So this salt increases the lipid solubility or the lipophilicity. Regardless of the polar group, it is the drug will be more lipophilic. We are going to see the reasons for making this to be more lipophilic. For lauryl sulfate, the salt formed between lauryl sulfate and erythromycin, erythromycin propionyl ester. When this R group is the propionyl group, this is the ester of the erythromycin. Now, when we form a salt of lauryl sulfate and erythromycin propionyl ester, one is called esterate salt, you can see that forming the ester here, this group increases the lipophilicity. And also addition of the stearate will form a salt, but though we have the sulfate group, this chain is more lipophilic. So this salt will be lipophilic. And there are higher chances that we shall have higher concentration in bile. You can have higher concentration in bile. So this lauryl sulfate salt can, or the esterate salt can increase the, can have higher concentration in bile, leading to, it can impede the bile flow, It can lead to cholestasis, hence leading to jaundice. So you can have the cholestatic jaundice. Due to higher lipophilicity of the esterate ester, you can have the cholestatic jaundice. And this can lead to idiosyncratic hypersensitivity. These higher lipophilic salts are made to mask the beta test. They are made to mask the beta test, the higher lipophilic salts. That's one. Another one is to increase the bioavailability, or bioavailability of these drugs increases. But you can have this adverse drug reaction. These ones, the more water soluble, or the hydrophilic, increase the water solubility, hence enabling the parenteral administration, the IV administration. That's all we can talk about the salts, I think. Okay, this lauryl sulfate, again, it is a suspension. It's a suspension. Of course, it masks the beta test. Yes, let's go to chemical properties where I have the acid instability. Yes, same kind of guy. About the chemical properties, we have the acid instability. For the macrolides, having the OH group at position 6 and a keto group at position 9, have cut this erythromycin below carbon 6 and below carbon 12. So those ones having the OH group and a ketone group at carbon 9, they undergo this mechanism. In presence of an acid, for example, in the stomach, this oxygen will attack the proton. We shall have attacking of the proton. It uses the electrons from one of the bonds, meaning that this carbon will stay unstable. When it's unstable, this oxygen now will come and attacks this carbon. That's what we have. So I can draw this structure like this. This is the carbon 6 here. I can have the carbon 7, carbon 8, then I draw my carbon 9. This is carbon 9. Then I have, this is carbon 11, 10. I have carbon 11, then I draw my carbon 12 right here. So it remains the same structure. Here I have a methyl group at carbon 6, and this oxygen has formed a bond with this carbon. So we have a bond from this carbon 9 forming a bond with this oxygen at carbon 6. We shall have that. Then there is OH group here. We have OH group at that position. And still, we have the hydrogen here on this oxygen. So it will be plus. I see. Then I have a methyl group here. Here I have OH group. I have a methyl group here and OH group. That's what we have. Then this oxygen is unstable. Now we shall have a proton shift. This oxygen will take this hydrogen. When it takes the hydrogen, this one will be stabilized, but this one will be unstable. So you can just show it like this. This one, when it takes this bond, this one gives the electrons to the oxygen to stabilize it. So we shall have this. We still have the methyl group there. This is O with 2 hydrogen atoms, but it's now unstable. We're having the carbon 10 now, carbon 11, and carbon 12 there. Here we have the methyl group and OH group. And a methyl group here. There is a methyl group at carbon 8 here. Still have a methyl group here, also here. This is, here is OH group. This is what we have. So this one, remember we have a hydrogen atom here. Here there is a hydrogen atom. Okay, this is the metal. We make this one the hydrogen atom. When this one breaks off as water, we shall have here loss of water. This carbon will be unstable. This hydrogen will now be lost to stabilize this bond. Therefore, we shall have this. This water is here. Loss of water is here because we lose water from this product we are going to see. Now we shall have this. We have formed a bond here. And we have a methyl group here. This is the carbon 9, carbon 10 and 11 plus carbon 12. We have OH group here and a methyl group. So we have OH here. Also, here we have a methyl group. Now, this bond, remember, we are under acidity. There is proton. This bond will attack the proton. When it attacks the proton, this carbon will be stabilized, but this one will be unstable. Now, this oxygen comes and attacks this carbon, which is unstable, stabilize it. Therefore, we shall have this. This bond is no longer there. You have a oxygen here, a methyl group, you have this. Also, a methyl group here, OH and methyl group. Now, this oxygen is unstable. We shall have loss of a proton. Let me draw it down here. Loss of a proton. So we shall have this. We have a methyl group here. Here there is still a methyl group. even here, also here. So this product is inactive. So in presence of an acid, for example, in the stomach, those tetracyclines having the OH group at position 6 and the ketone at position 9, they undergo this mechanism, the X of the erythromycin. Therefore, these tablets or these drugs are made to be enterically coated. They are made to be enterically coated due to the inactivation by the acid. Also, there are some analogs, the erythromycin analogs, which are made such that either there is no this ketone at position 9 or there is no this OH at this position, as we are going to see here in the analogs. We are going to see if there is no ketone here and there is no OH group here, one of them leads to the stabilization of these drugs. This is the cyclic. It is the cyclic keto formation. As you can see, these two groups, as if this is a furan and also this is a furan. So these two furan rings, it's what we call the internal cyclic keto formation. This is the formation of the inactive compound. Hence, these drugs are not stable in the acidity of the stomach. Let's go to the mechanism of action.